Welcome to This Explainer. Today, we're diving straight into the absolute chaos of Earth's weather and the stunning 2025 and 2026 AI revolution that's finally learning how to tame it. You know, weather shapes virtually every single aspect of human civilization. We're talking about everything from the food on our plates to the multi-billion-dollar disasters we have to endure. But how does it actually work? And how on earth are we suddenly predicting it with such unbelievable precision?
So let's kick things off with a pretty massive question. What actually powers the incredible, often destructive force of the weather systems we experience every single day? Because before we can wrap our heads around the artificial intelligence that predicts a hurricane, we really need to understand the planetary machinery that builds one in the first place.
Here's our roadmap for this explainer. We're going to hit the global weather engine, the atmosphere in motion, anatomy of extreme weather, the AI forecasting revolution, and finally, weather in a changing climate. Let's get right into it.
Section 1. The global weather engine. This is what fuels the chaos.
Right off the bat, there's a crucial distinction we need to make. It gets mixed up all the time, but scientifically, it's very precise. Basically, you can think of weather as the atmosphere's mood on any given day. Climate, on the other hand, is its long-term temperament over 30 years or more. So weather is what you get. Climate is what you expect. A random blizzard in April, that's just a bad mood. A consistently freezing winter over decades, that's a temperament.
So what actually fuels this massive planetary engine? Well, it's driven primarily by the sun, which heats the equator way more than the poles. This forces the atmosphere into this constant, desperate struggle to balance out that extreme temperature difference by shoving heat poleward. Throw in the latent heat, which is essentially stored energy inside water vapor, and our natural greenhouse effect, and you've got a powerhouse. By the way, without that greenhouse effect, Earth would be freezing at minus 18 degrees Celsius instead of a comfortable 15. Together, all of this provides the raw energy for every gentle breeze and raging storm.
Moving on to Section 2, the atmosphere in motion. Let's talk pressure and spin.
You can basically think of our atmosphere as a giant, endless turf war. On one side, you've got high-pressure systems, anticyclones. This is where sinking air compresses, warms up, and gives us those nice, clear, calm skies. On the flip side, we have low-pressure systems, or cyclones, where rising air expands, cools, and wrings out its moisture to form clouds and nasty weather. And here's the rule. Air always wants to rush from high pressure over to low pressure to balance things out. But here's the catch. We live on a giant spinning rock. So that moving air, it never flows in a perfectly straight line. Because the Earth is rotating right beneath it, we get the Coriolis effect. It curves the winds to the right in the northern hemisphere and to the left in the southern hemisphere. It's this invisible, fictitious force that explains exactly why storm systems rotate, why hurricanes have that iconic spiral shape, and why we have those massive, meandering jet streams way up high. Now, if we zoom way into a microscopic level, rain doesn't just spontaneously fall out of the sky. For a cloud to even form, air has to cool down to its dew point. But even then, the water vapor needs something physical to grab onto. We call these cloud condensation nuclei. It's literally tiny specks of dust, industrial pollution, or sea salt. Without this microscopic debris floating around, clouds as we know them wouldn't even exist. Pretty wild, right? Okay, zooming back out to the size of a continent, we can actually map the exact 5-step life cycle of a mid-latitude cyclone. These are those sprawling, massive storms that dictate daily weather across places like North America and Europe. They kick off as just a small kink where cold and warm air clash. They deepen into a fierce low-pressure center, hit a violent mature stage, and then finally suffocate themselves. That last stage is called occlusion, and it happens when the faster-moving cold air literally undercuts and completely cuts off the warm air.
Which brings us to Section 3, Anatomy of Extreme Weather. We are talking about unimaginable power here. 30,000 Kelvin. I really want that massive number to sink in for a second. Inside a supercell thunderstorm, ice crystals and soft hail are constantly, violently colliding, creating this huge electrical charge separation. When that charge finally snaps and breaks the air's resistance, the lightning bolt heats a super narrow channel of air to 30,000 Kelvin in just microseconds. That is literally 5 times hotter than the surface of the sun. And it's just happening right above our heads.
Or consider this absolute jaw-dropper from 2025's historic Hurricane Melissa. During the peak of that monster storm, a dropsonde, which is a really specialized instrument that hurricane hunter aircraft drops straight down into the storm, recorded an unbelievable wind gust of 252 miles per hour. That's the strongest wind ever measured by one of those instruments. It really shows you the terrifying upper limits of Earth's weather engine.
But here's the thing, monster storms like Melissa don't just pop up out of nowhere. They need a highly specific, almost perfect recipe to get their engines going. You absolutely need ocean waters of at least 26 or 27 degrees Celsius for fuel. You need high humidity so the storm doesn't dry out. You need really low wind shear so the thunderstorm towers don't get ripped apart. And you need just enough planetary spin from our good friend the Coriolis effect. If even one of those ingredients is missing, the hurricane just cannot form. No exceptions. All right, let's pivot to Section 4, the AI forecasting revolution. Enter the 2026 Oracle.
This right here is the massive paradigm shift that completely disrupted meteorology in 2025 and 2026. For 70 years, we relied on brute force supercomputers. They would crank through incredibly complex fluid dynamics and physics equations over several hours. But the new AI models, totally different playbook. They use deep neural networks trained on decades of historical data to just instantly recognize patterns. This lets them map out the next 10 days of global weather in under 60 seconds, all while using a fraction of the energy. And the speed of this revolution has been nothing short of staggering. This wasn't some slow, gradual rollout. In November 2023, Google DeepMind drops GraphCast. Boom! By early 2025, Europe's premier weather agency makes their AI model AIFS fully operational. Right on their heels, NOAA launches their AI-driven ensemble models in the US. And then by 2026, scientists are already testing real-time global forecasts at an astonishing 3-kilometer resolution. That is so highly detailed, they can literally pinpoint individual thunderstorms anywhere on the planet. The efficiency gains we are seeing across these models are basically magic. GraphCast actually outperformed the gold standard physical models on 90% of its targets. AI Fast achieves its accuracy using 1,000 times less energy than traditional physics-based models. 1,000! And NOAA's AI GFS requires only 9% of standard computing resources. We're drastically lowering costs while actually buying ourselves more warning time for extreme events. It is a total game changer for disaster preparedness.
Finally, Section 5, Weather in a Changing Climate. We need to talk about the compound risks we're facing. Because here is the harsh reality. Global warming isn't just this slow, even, predictable temperature bump. It's driving a nearly 8-fold increase in what scientists call compound extreme events. Back in the early 2000s, these events happened at a rate of 1.6% per degree of warming. By 2025, that number shot up to 13.1%. This means that devastating droughts and lethal heat waves aren't just happening more often. They're teaming up and striking at the exact same time, multiplying the threat to our food, our infrastructure, and to human life.
So, what does this mean for that global weather engine we talked about earlier? Well, our oceans absorbed record amounts of heat again in 2025. That heat acts like high-octane fuel, directly driving the terrifying intensity of storms like Hurricane Melissa. Meanwhile, the Arctic is warming 3 to 4 times faster than the rest of the planet. And since the temperature gap between the equator and the poles is what drives our winds, a rapidly warming Arctic threatens to stall out the polar jet stream. It's basically causing our weather systems to get stuck in traffic, which prolongs deadly heat waves and devastating floods.
As we wrap up this explainer, I want to leave you with a defining scientific debate of 2026. We are literally watching a collision right now between a rapidly changing, increasingly chaotic atmosphere and the most powerful predictive technology humanity has ever built. So the big question is, as our climate shifts into completely uncharted territory, will pure artificial intelligence become our ultimate weather oracle? Or will we always need the foundational laws of physics to guide us safely through the storm? It's a fascinating frontier. Thanks so much for joining me on this deep dive.